In the last lecture, we discussed about chemical equilibrium. We understand what chemical equilibrium is. Let's dive more into understanding of term equilibrium and types of equilibrium. Equilibrium is described as the state in which measurable properties, such as position, speed, temperature, concentration, and pressure, remain constant over time. There are various types of equilibrium, including physical equilibrium, thermal equilibrium, mechanical equilibrium, and chemical equilibrium, among others. Thermal equilibrium occurs when two or more substances reach a state where their thermal energy is balanced, meaning they have the same temperature and no heat flows between them. Here are some real-life examples of thermal equilibrium. Hot coffee in a room. A cup of hot coffee eventually cools down and reaches the same temperature as the surrounding air, achieving thermal equilibrium with the room. Refrigerator cooling items placed in a refrigerator eventually cool down to match the refrigerator's set temperature, achieving thermal equilibrium with the environment inside. Physical equilibrium. Physical equilibrium refers to the state of balance between different phases of the same substance, where no chemical composition changes occur. In this equilibrium, the substance exists in different physical states, while maintaining a dynamic balance between them. Solid-liquid equilibrium. Example: H2O, solid, in equilibrium with H2O, liquid. At the melting point, ice turns into water at the same rate that water freezes into ice. And this balance is called solid-liquid equilibrium. Liquid-vapor equilibrium. Example: H2O, liquid, in equilibrium, H2O, vapor. At a given temperature, water evaporates, turns into vapor, at the same rate that vapor condenses, turns into liquid. This balance is called liquid-vapor equilibrium. Conditions necessary for liquid-vapor equilibrium. 1. Closed system. The system must be sealed, so no matter can enter or leave. 2. Constant temperature. The temperature of the system should remain steady. 3. Stable properties. The observable characteristics of the system should stay unchanged over time. 4. Solid-vapor equilibrium. Some solid substances, when heated, directly convert into vapors without going through the liquid phase. This process is known as sublimation. When the vapor cools down, it changes back into the solid state, a process called deposition, desublimation, or simply reverse sublimation. For example, ammonium chloride, NH4Cl, undergoes sublimation when heated. NH4Cl, solid, in equilibrium with NH4Cl, vapor. Upon cooling, the vapor condenses back into solid ammonium chloride. Equilibrium between a solid and its solution. When a solid solute is in contact with its saturated solution, a dynamic equilibrium is established between the solid phase and the solution phase. Solid substance, in equilibrium with solution of the substance. Example: sugar in a sugar solution. In a saturated sugar solution, a dynamic equilibrium exists between the dissolved sugar and the undissolved solid sugar. Sugar, solid, in equilibrium with sugar, aqueous. At equilibrium, the rate at which solid sugar dissolves into the solution is equal to the rate at which dissolved sugar precipitates back as a solid. This means the number of sugar molecules entering the solution equals the number of molecules leaving it, maintaining a balanced state. Equilibrium between a gas and its solution. In a liquid. When gases dissolve in liquids, the solubility of the gas in the liquid depends on several factors. Key factors affecting gas solubility. 1. Nature of the gas and liquid. The chemical properties of both the gas and liquid determine how well they interact and mix. 2. Temperature of the liquid. Higher temperatures usually reduce the solubility of gases in liquids. 3. Pressure of the gas. Above the liquid. The solubility increases with higher gas pressure over the liquid's surface. This type of equilibrium is explained by Henry's law, which states, the amount of gas dissolved in a liquid at a given temperature is directly proportional to the partial pressure of that gas above the liquid. However, as the temperature rises, gas solubility typically decreases. Additional concepts. Normal boiling point. For any pure liquid at 1 atm pressure, the temperature at which the liquid and its vapor are in equilibrium is known as the liquid's normal boiling point. Supersaturated solutions. When a solution becomes supersaturated, equilibrium cannot be observed until some of the excess solute precipitates out or dissolves further. Dynamic equilibrium in precipitation. At equilibrium, the rate at which molecules precipitate from the solution is equal to the rate at which they dissolve into it. Thank you for watching. If you found this video helpful, don't forget to give it a thumbs up and hit the subscribe button to stay updated with our latest content. In the next video, we'll dive into the topic of chemical equilibrium expressions and explore their derivations step by step. Stay tuned, and I'll see you in the next one.